See that online? Oh, well, there's another loop there now.
Yeah, you are actually, so everyone else has big trouble.
Good afternoon, everyone. Welcome back to the Nuclear Engineering Department seminar series. It's my pleasure. So I'm Igor Polotov. I'm professor in nuclear engineering here, in case you don't know me. So it's my pleasure to introduce Dr. Naveen Pillai, who is locally visiting us. So he was getting his PhD with me and then Professor Katarina Stekelman over the past 4 years. And in the past few couple of months, right? So he's working with us as a postdoctoral research associate. And before that, he got his bachelor's degree from Department of Chemical Engineering, Material Science at the University of Minnesota. And he's actually focusing on multiphysics framework improvement, which we're going to talk about today. Please welcome Naveen Pillai.
Thank you for the introduction, Dr. Blatno. As Dr. Blatno mentioned, I'm going to be discussing a multiphysics framework that I developed over the course of my PhD. And at the end, I'll be briefly discussing kind of where we're going with that. And so typically, this discussion or this presentation leads to a lot of questions and excitement. And so I'll try to keep it a little shorter than usual. So we'll see how that goes. Brief outline of what I'm going to talk about. It's pretty standard. So I'm going to introduce the topic and the motivating background. And then I'm going to discuss how DNS is involved. And then briefly foray into the long-term applications we had going into the project. And then at the end, we'll see some applications that we noted going out. And then I'll go over the methods, show some results, and then conclude the work. On the right here, you see just kind of a sample image, just to kind of condition you to the simulations we'll be seeing. And so there's an air-filled pipe with air flowing in on this side, and bubbles are forming and rising. The vortices you see up at the top are visualized using the Q criterion, which is just a mathematical way of quantifying the vortices, and the regions shown are where the vorticity is higher than the strain rate. So some of the motivating background for this project was to essentially look at a better way to have plasmas ignite near a liquid interface, because plasma and liquid interactions have a variety of applications. So for example, the initial motivating application looked at producing fertilizer from water and air, and then there's a multitude of applications looking at decontamination of water. And with a lot of these applications, the surface to volume ratio of the plasma at the interface plays a big role. And so adding bubbles in could help to maximize that ratio. Something that's been noted in the past is that direct ignition in the liquids is challenging, and if you wanted to ignite a plasma in a pure liquid, typically you would end up superheating some of the liquid, or there'll be micro bubbles, and that's really where plasma would show up. But we've also noted that computational investigations have shown that we can have stream breakdown in bubbles due to where the electric field is enhanced due to permittivity differences. So that's what this slide is about. You see here at the top left, there's an applied electric field of 40 kilovolts per centimeter. So these simulations are in 2D. So there's just a plate at the top and a plate at the bottom. And just on the right there's a bubble that has kind of a realistic aspect ratio. So if you took that aspect ratio scaled to 3D, that's kind of the aspect ratio we see in simulations and experiments. But just based on the work in this paper, they noted up to 10 times electric field enhancement in these ellipsoidal bubbles. And while we might not see that in 2D based on our shapes, in 3 dimensions, we think that we might actually see a comparable electric field enhancement. But that's kind of some of the work we'd like to do in the future. So to target those ellipsoidal bubbles, we need to look at a map like this to kind of determine, the properties of the fluids we want to mess around with. So rising bubbles in fluids take on a variety of shapes based on the Edvos number on the top left, which is a dimensionless number, and the Galilei number. And there's some nomenclature there if you're interested. The key point here is that we're focused on this parameter space, and that's just simple water, room temperature, and simple air. And that would lead to bubbles being formed in that region. You'll see that's in the ellipsoidal region of this phase diagram. And all of those bubble shapes have actually been validated in FASTA from another student of Dr. Blodno's. And so that's just to show that the interface tracking we use in FASTA is pretty good and can capture these pretty weird shapes and resolve them. So the long-term application I mentioned that motivated part of this beginning of this work is plasma production, plasma treated water in fertilizers, and really to generate some nitrates into the water and perhaps some other reactive oxygen and nitrogen species. But really in this presentation, you'll be seeing, we just talked about that plasma liquid interface and just looking at how the bubbles form and then what happens in the bubbles. And I don't really go into any chemistry in this presentation. So I'm going to go over the methods from the DNS point of view. And DNS is direct numerical simulation. If you haven't heard before, it's a highly resolved set of CFD. So the code we use is called FASTA, and it's been developed for about 20 years. And it's basically a direct way to solve the Navier-Stokes equation. So DNS used to stand for, at one point in the past, direct Navier-Stokes, and then it later got changed. But the main distinction typically between DNS and say higher resolution CFD is that there's no turbulence modeling. And really, there might be DNS purists out there where there's no modeling done in DNS, and you're just taking the Navier-Stokes equations and solving them and trying to resolve all the physics using that without any additional modeling. We definitely haven't got there in this work, but for the bulk regions of the fluid, you'll see these equations being solved without turbulence modeling there. Yeah, quick buzzwords with FASTA. It's 3D, unstructured grids, finite element method. So this is some examples of some of the work that's been done in the past using FASTA and in our group. And these studies have been picked because they have some relevance to this project. So we've got a multitude of bubbles flowing in a liquid. These are droplets colliding into a spacer grid. So that's the resolution of the kind of an interface against a solid. And droplets are harder to resolve than bubbles. And so seeing this done makes the bubble side of the equation a lot easier to deal with. And then there's this bubble-induced turbulence. And so kind of looking at the weights of the bubbles, if they were very aggressive, FASTA would be able to deal with that as well. But typically with our bubbles rising in quiescent fluid, it's just laminar flow behind the bubbles. And so it's not a big deal to resolve. We're more interested in the collision side of that. So the simulations were based on an experimental setup that we have in-house at NC State. And these experiments were performed and developed by Nick Sponsel, who's a grad student. And he's built a fish tank with a metal pipe in it. And air is basically flowed into the side of that metal pipe and rises through. And he takes pictures like this to provide information for DNS. And so this is roughly what the domain would be like for the simulations as well. So I'm going to quickly go over novelty of the fluid dynamics aspect. So typically when there's like an orifice problem, and this is studied well in the chemical engineering side of the world, the orifices are usually a little bit bigger than the 0.5 millimeter orifices we have. But they're also flat, so it'll be a flat plate with holes drilled in it, and the air would be coming in from the bottom rather than from the side. And then you'd see a multitude of bubbles going through, and that's used for example, bubble column reactors and things like that. But also the orifices are typically not that small. 0.5 millimeter is like smaller than, or of the order of the tip of your pens. That's it's a really small size to resolve, in addition to a kind of large pads of the bubbles. So here's like a whiz through of kind of the scale of the meshes I've dealt with. So from the order of 4 million elements to about 700 million. And so where we're looking at the orifices, there are kind of multiple layers of refined regions, where you have the finest region in the center and it kind of graduates out. But I'm going to focus more on the biggest mesh because that's the coolest case. And so you'll see that mesh here. And so this mesh has a few things going on. So if you zoom in over here, there's actually 2 electrodes. And then over here, you can see the side of the electrodes. And so the electrodes have this boundary layer near them. So the mesh at the wall starts at 10 microns. And it graduates out to the bulk mesh over here, which is on the order of 80 microns. And then over here, we see, again, that boundary layer near the sides of the wall. So in terms of setting up this case, it's really expensive to look at the bubble formation at the orifices as well as bubble collision at the electrodes, because when the bubbles are rising, your simulation is going to be limited by the time steps required to resolve the formation at the orifices. And then once the bubbles start colliding, that could also slow the simulation down. So rather than having both those going on at once, I did a set of simulations looking at the bubble formation, and then another set looking at the bubbles colliding with the electrodes. And so that way, when the bubbles are rising before they hit the electrodes, we don't have to deal with the formation part, but then it's a question of how do we get the right shapes, sizes, positions of the bubbles. And so that's what the experiments were used for. So Nick would take images like this, and they take multiples of them over target flow rate. So for this case, it was 700 milliliters per minute. And then these images would be characterized using MATLAB code, and the data would be processed. It would be something like 25 to 50 images like this would be taken. The bubble shapes and positions would be taken through, sorted, averaged. And then we'd get something like this for the equivalent diameter of the bubbles versus the distance from the nozzle. So this is the nozzle down here. And if you see here, the equivalent diameter appears to decrease as the bubbles rise, which doesn't make sense because if anything, the diameter could increase as the bubbles might expand, but we're talking like only millimeters of bubble path. So even that, in that distance, you wouldn't even expect the bubbles to expand. So you won't see a straight line. So what's going on here is actually we have a 2D bubble projected, a 3D bubble projected onto a 2D plane. And so when that happens, as the bubbles shrink from spheres to ellipsoids, we start to lose more of the bubble mass, which is reflected in the equivalent diameter. And so an equation can be used to correct for that phenomenon. And when I do that, you'll see something much more resembling a straight line as the bubbles rise above the nozzle, which is what we would expect. And then we can use the aggregated data from the experiments to seed these bubbles based on the positions, sizes relative to the nozzles and to each other. And so we get a pretty good initial condition for these simulations. So now I'm gonna go over the results I've seen in fluid dynamics, and I'm gonna start back at the bubble formation step. So we looked at experiments at 50 milliliters per minute and compared it with our simulations to see if the eccentricity, which is essentially how deformed the bubble is, looking at essentially is it a sphere or is it an ellipsoid, and looking at that axis. And we found that the experiments and simulations trended towards an eccentricity of 0.9, which was pretty good agreement. And so we also looked at something more qualitative like this. So again, with experiments at 50 milliliters per minute and simulation at 50 milliliters per minute, you can see bubbles forming and reaching the same shapes, sizes, positions as the experiment, which was a good sign. And we also noted that within the bubbles, and so this is something you can only do via DNS, there were some velocities, there was some recirculation happening where the velocity distribution wasn't homogeneous. And so you'll see here that the y velocities are scaled within the bubbles. And you can see the recirculation shifting the bubbles momentum from the center to the edges back and forth, which results in the edges of the bubbles flapping a little back and forward as these bubbles redistribute their momentum. And so to look at this in a more quantitative fashion, I have another slide. So I split the bubbles into thirds. Thirds in one dimension. So, but 50% of the bubble mass would be in the blue region and 50% of the bubble mass was in the green region. So the sides and the center. And this was to look at, to quantify essentially the differences in bubble momentum from the center and the sides of the bubble. And so if we just look at one bubble and look at the momentum fraction, so this is normalized to the the main bubble momentum. See that the center initially starts with a high relative amount of momentum, and it oscillates and levels out at slightly above half the bubble's momentum, whereas the sides start with relatively low bubble momentum and then oscillate towards just below half the total bubble momentum. And this is true for all bubbles, but it's easier to see just one at a time. So looking at the airflow at more than one orifice now, we can see some interesting trends. And so this slide has a little bit of flashing, so if you're sensitive to that, you probably want to look away right now. And so at the top, you can see an overview of the flute. And then you can see the 5 orifices over here and the airflow coming in through the side. And so you can see the air redistributing across the orifices as time goes on. And as departure events happen, see more redistribution. And so once again, we can look at that more quantitatively in a slide like this. So this is looking at the Z flow. So that's the flow across the nozzle, and the positive Z direction is this way. So before the nozzle, this should roughly equal to your inflow rate. And so we see that consistent 500 milliliters per minute seen there. And then for the second, third, and fourth nozzles, we see that some of the air goes through the second nozzle, some goes to the third, but almost no air makes it to the last nozzle. And so when I do further analysis, I neglected the fourth and fifth nozzles as there's very little air going through. And you would have seen that in the previous slide where the last 2 nozzles were black. And so looking through at the rise velocity or in the vertical direction, you can see some interesting behavior in the vertical flow fraction, which is the proportion of flow allocated to the relevant nozzles. And you can see some fluctuations there, which I've attributed to departure events or pinch-off events that's happening at the nozzles. And so what happens then is there's more surface tension at the nozzle front. And so the bubble, there's more pressure there. And so the airflow moves on to another nozzle and the bubble is formed somewhere else. And so, for example, over here, you can see there's this instantaneous drop in the flow fraction of the second nozzle and a rise in the flow fraction at the first and third nozzles. And if you zoom in, you can see that there's a departure event that occurs, pinch-off event. And once again, over here, we can see a departure event where there's an instantaneous drop at the third nozzle and then a rise at the other two. And sure enough, we see that in the data. And then at the first nozzle now, we can see a departure event where there's an instantaneous drop in the flow fraction and a rise in the flow fraction of the other two nozzles. And then there are several other departure and pinch-off events that I've highlighted there. So another thing that we need to stay aware of was the volume conservation. So the level set method that I used to track the interfaces is known to not conserve the volume or mass perfectly. But I made this comparison to make sure that this mass loss, if any, tracks with the instantaneous flow. And so we're not getting, for example, disproportionate mass loss where there's more flow in nozzle one or anything weird like that, more that it's consistent and due to the level set method across all the bubbles. And we do see that on the right here, where the instantaneous flow is matched by the piecewise measured volume. And we do note that over the entire simulation, about 20% of the volume is lost to the way the interface is redistance over each time step. But that is fixed in a later simulation, which is this one. So I looked at bubbles colliding with the electrodes. And so over here we have kind of a 3D side view. Over here, just a 2D top view of the bubbles rising into the electrodes. And then this is kind of like a front view, the front of the fish tank. And again, these are the bubbles I seeded from the experiments at 700 milliliters per minute. And so over here, you can see the bubbles rise and then collide into the electrodes, and then some of them carry on past the electrodes. But you can also see some bubbles just absolutely smash into the electrodes and are kind of stay there until the end of the simulation. So I'll play that for you once again. I'll watch the bubbles rise. Some of them manage to hit the electrodes and sneak past, while others kind of are stuck there. And so I used this simulation to generate images to look at the bubble shapes near the electrodes, which we'll see in the future. Before that, I'm going to just look at the bubble rise velocities to kind of search for any trends. And what we see is right around 60 milliseconds after the simulation, the bubble rise velocities start to go kind of all over the place. And so we see that both in terms of the rise velocity and the eccentricity, where the eccentricity peaks, which we noticed in the experiments at 50 milliliters per minute, and starts to spread out. And that is also matched with kind of a fluctuation, the bubble rise velocity. In terms of the X and Z velocities, so to recap, the Z velocity is kind of along the electrodes and the X velocity is orthogonal to the electrodes, and both of those are orthogonal to the vertical direction. If the electrodes are here, you see kind of the bubbles going more or less on either side of the electrodes, with individual bubbles swinging a lot, which is to be expected, both in terms of the X and Z direction. Initially, there is a little bit more swing in the Z direction, but then we see the bubbles kind of cross back over, and the same is true for the X velocities. So back to the volume conservation, this time I implemented some work done by, I believe, Dr. Jing Fang which essentially tracks the rate at which the interface is artificially moving backward and then pushes it back forward to essentially attenuate and hopefully completely eliminate the volume loss we see due to the level set method. And you see that being achieved pretty effectively here, where the simulation void fraction is the same as the starting void fraction throughout the domain. And we can track that for individual bubbles too. So excepting for coalescence events, which occur here and here, the bubbles maintain the same size and volume throughout the simulation. And when bubbles coalesce, you can see that they in fact get bigger. And then the bubbles that existed before the coalescence disappear out. And so an important thing to do here is to validate the shapes of the bubbles. And the main reason for this is because I started with spherical bubbles in the middle of the domain as opposed to what we see in the experiments, which would be some air forming into bubbles that are initially spherical a little lower down. So what we see here is a bit of a jumbled mess, but we see the DNS data more or less tracking where the experimental data is. And so if we look at that in a more statistical fashion, we can see some confidence intervals here and see a decent amount of overlap. I think the best way to visualize this is on this slide, where we plot the paths of the individual bubbles over space and compare it with the 95% confidence interval for the experiments. And what you see is that while some of the red and green bubbles, which were the higher bubbles up that experienced a more unnatural wake, are deformed more because they experience more acceleration initially because there's no wake in front of them. Whereas all of the blue bubbles, which are the bottom layer, which experience the wake of two bubbles above them, fit within that 95% confidence interval, both in terms of eccentricity and the individual ellipse parameters A and B. And so this is good because then we can be more confident that the shapes of the bubbles, or at least the aspect ratios going into the electrodes. And then we can use that data to transfer the information over to a plasma code. And so this is the multiphysics framework I've developed. And so on the far left, we have a picture from 3D DNS. And so what I do is I take a slice of that simulation, colored in black and white, where the black is the liquid, the white or the light gray is the gas. And then there's a dark gray that represents kind of the non-domain or the solid. And then you can trace that slice, create a mesh on it, and then essentially solve the equations for plasma hydrodynamics in a separate solver. And so you can see, for example, the 2D potential in that same bubble picture here, and then even 2D streamers. And so one thing that might come to mind when we're looking at this is, does the bubble move while we're doing the plasma simulations? So here's a slide showing the relative timescales for those simulations. So the plasma simulation time steps are on the order of 10 to the minus 14 to the 10 to the minus 12 seconds. And the voltage pulses that we use are on the order of nanoseconds. And this is in the simulations. Whereas the DNS time steps in the simulations are on the order of microseconds. So to put that in perspective, if I were to rescale plasma simulation time steps to be on the order of half a second to a minute, then the voltage pulses would be on the order of 1 to 10 days. And then the DNS time steps would be on the order of a PhD. So these bubbles are not moving due to the regular fluid dynamics over the scope of the entire plasma simulation. So I'm going to move on to the plasma hydrodynamics now. So I'll introduce the solver, the geometry, and then move on to some cases. So there were kind of two phases in the plasma simulations that I did. And so the first phase was kind of a preliminary phase, looking at the different geometries, what might be the best geometry to do these simulations in. And then the second phase was, once we identified a good geometry, was to use DNS to look at what happens in those bubbles. So the plasma hydrodynamics code I used was called nonPDPSIM, which was developed by Dr. Mark Kushner. And it's about 20 years old as well, and his group at the University of Michigan. So that solves for the plasma in a fluid as a fluid. So there's charge conservation, charge species conservation, the electron energy equation, and a whole lot of chemistry that happens in the back end. So I looked at 3 geometries in 2D Cartesian simulations. So the first geometry was kind of, I think, our initial targeted geometry, which was having that pipe in the middle be charged where the air is coming in, and then having a ground, whether that be copper or something else, around that pipe, creating something like a wire to cylinder type electric field. And then in those simulations, we saw that streamers wouldn't form in the bubbles near the pipe, they would in fact form in the bubbles at the pipe, which meant that the plasma could also then go on vacation through the airflow tube, which is in fact what we saw, and that's why Dr. Stockman is laughing. So that's obviously dangerous. We didn't want to go further with that. So from the simulation perspective, it might be interesting, but for experiments, we axed that. So the next thing we looked at is, okay, so what happens if we don't charge that pipe and in fact add another electrode in the middle and charge that? So I have some simulations of that. And then there's another geometry we looked at is what if we have two electrodes floating in the middle of the tank, and we charge one of them and then we ground the other. And I have simulations looking at that as well. So Nick has once again produced some wonderful experimental images showing that without bubbles passing between the electrodes, we do see some plasma activity. It's not nothing. But then once we do have bubbles passing between the electrodes, you definitely see way more plasma activity, so much so that you can see the reflection of that in other bubbles. And so we can clearly see that the bubbles are enhancing the electric field or the potential for plasma to form in the space between the 2 electrodes. So the initial conditions and the setup for my case was for the plasma hydrodynamics, was as follows. So I filled the bubbles with humid air. So that's 2% water and your regular oxygen nitrogen distribution. And then I threw in a very small fraction of electrons, oxygen, and nitrogen ions, just to have a kind of a seeded start. And there's some thought of some amount of background radiation creating like some amount of background ionized species, and we're not really sure exactly what creates like an initial amount of plasma, and this is on the order of 10 to the 8 centimeter cube, so it's a very minute amount, and the amount that we expect is even smaller than that, but for this simulation we require a little more. And that's just to get the simulations kickstarted. And then the conductivity of the water is 35 microsiemens per centimeter, something like that, what you see in some deionized water. And the water is treated as a lossy dielectric. And so on the timescales that we see, which is on the order of nanoseconds, the water more or less does act like a dielectric. And so we don't really look at ionization or anything there, but we could in the future, especially if we're interested in different timescales where the lossy dielectric approximation is no longer valid. And the voltage pulse I use is pretty straightforward. So I just ramp up the voltage to the max in 1 nanosecond, and then we leave it there for the rest of the simulation. This 30 kilovolt is something that I did initially, and that was also when we had plasma running down air pipes. But I do something more like 20 kilovolts or 24 kilovolts with some of these other bubbles. And so you might be wondering, how do these 3D domains translate into these 2D domains? And so you can see these bubbles are oblate spheroids. So that means the longer axis is in 2 dimensions. So there's it's kind of like a disk, essentially like a fat disk. or like a hamburger. And so if you cut it that way, you can get a slice like that. And then if you cut the domain along the vertical direction like that with an electrode, you can get a slice, something like that, if a bubble were to reach into it. And so those transition into domains for nonPDPSIM for the plasma hydrodynamics modeling. And so we have the water as a solid dielectric, the ground in yellow, either surrounding the tank or just in surrounding the tank and in one of the electrodes in the tank, and then a powered electrode and then your bubble. And in these simulations, we do have the glass in the middle, as that's what we have in the experiments too. And these length scales are on the order of centimeters in case you want to get a gauge how big these things are. So this is a 3.2 millimeter electrode in these bubbles. This gap is 5 millimeters. So for the computational folks in here, this is bubble mesh. And so if you zoom in on the electrode to bubble section, you can see there's some nice boundary layers of the mesh. So we have rows of equidistant nodes that better capture the fluxes going into and out of these shapes. And we see that for this simulation as well. So one of the things we're interested in, as I mentioned in the beginning, is the electric field enhancement that we see in the bubbles. And so where you might see kind of a weaker electric field in the surrounding liquid, you see electric fields of up to right about 30 kilovolts per centimeter in the bubble. And it's in those regions where you'll see the streamers start to develop. And this is with 12 and 18 kilovolts. We see a similar story with the bubbles that are near the electrodes. And so this is that wire to box geometry that I discussed. And these three, where the bubbles are kind of up against the electrode with a thin liquid film, only 12 kilovolts is needed to see streamers form. But once the bubbles are a little further away, slightly higher voltage is required. So 24 kilovolts is about the lowest I needed to see plasmas forming. So I'm just going to show you the streamers forming in a bubble. So you can see that the electron avalanche travels from the opposite side, and so the positive streamer goes through and then along the surface. And so for those of you that are not totally used to seeing streamers, I have something that might help. So the electrode is positively charged. And so if we're just looking at the total charge, what's going to happen is the electrons are going to be attracted to that giant positive electrode and leave positive space charge in the bubble. And then as there's positive space charge in that bubble, electrons, once there's enough positive space charge, electrons are going to attract to that positive space charge. And then cause positive space charge where the electrons left. And so you'll see that kind of thing happening here, which eventually results in a positive streamer along the edge of the bubble, and then some electrons kind of following there. We can also look at the source term for electron impact ionization, and you see that majority of the ionizations that are happening in the initial part of the simulation is due to electron impact. And then once bubble hits the wall, that term becomes exceedingly high, as we see by the pure red, which is the max source term. And then we can also look at the electric field evolution through space. And once again, as the streamer forms, the electric field at the head of the streamer is remarkably high. And then as it dies out, the streamer dies out. So a quick comparison with experiments. So once again, these experiments were done by Nick, and there's a variety of images here. And so this is your general scale of electron density, ranging from a log scale from over 3 orders of magnitude And so this is a 20 nanosecond simulation. You see a stream running all the way across the bubble. And here's a 2 microsecond exposure of the bubble. And so if you flip that, it kind of vaguely looks like this. And then if you zoom in, you can see that these images have some kind of resemblance where it's kind of like a high amount of electron density and therefore light emitted kind of at the tip. And there you can kind of see the path it's taken over here. And you can also see potentially a volumetric type discharge where the bubble is a little bit more spherical. And so I used an actual circle in my 2D simulation. But this is a little bit more spherical bubble where the discharge actually goes through the volume of the bubble rather than along the edges. So some conclusions. I've used DNS to validate the formation and evolution of millimeter-sized bubbles in water, as well as tracking the aspect ratios and eccentricity of those bubbles, which peaks at about 0.9. And then the bubbles seem to flap their edges with the recirculation, and the internal velocities are different. An information transfer scheme has been developed to use to successfully import the 2D shapes into these plasma simulations from the DNS, including bubbles near electrodes. And so these simulations have been used to design experimental setups, saving potentially lives, time, and money. And these have been now focused on having either powered electrode above the bubbles and a grounded electrode around it, or 2 electrodes with 1 powered and the other grounded. And in these simulations, we typically saw streamers propagating on the surfaces of the bubbles, especially when they were deformed. And so I'm going to go over some quick applications, why we're interested in the future of multiphysics like this. So this is some work done almost 7 or 8 years ago now in Dr. Foster's group at Michigan. And they like destroying bubbles. So what they do is they levitate the bubbles in water using sound. And then they attack them with an electrode. So the electrode's over here, 0.5 millimeter gap. And you see that after they turn it on, the bubble gets attacked and then destroyed. And so this could be something cool to try and simulate. Some more reasonable applications of this rather than destroying bubbles are seen in the medical field, and Dr. Stoppelman does a lot of this type of work as well, where we see highly asymmetric 3D discharges, say between electrode and skin. And then some of the more historic work that's been used with these idealized 2D solvers is electrospraying, but we might see if, for example, you had a asymmetric substrate or something like that, you might have a need to look at that in 2D as well. Julius, a student of Dr. Krishner, has also looked at essentially activating catalysts in slurry reactors using a plasma, which is like a 4-phase problem. But that's something that's pretty interesting. And so some acknowledgements real quick. So my PhD advisors obviously contributed a lot to this work, as well as my PhD committee. Dr. Doster, Dr. Fang, Dr. Krishner, and Dr. Shannon, who's here. And then Nick Sponsel and JT Mast have helped me with providing experimental images and some experimental data. And Dr. Krishner and his group at Michigan, especially Julius, have helped me learn the code nonPDPSIM and obviously allowed me to use it, which you've seen in these simulations. And then here are some libraries we used in fast symmetrics and Altair. The computing facility at Argonne have allowed us to use their machines, CDIS and Theta to run these cases on, and Cooley to visualize the cases. And then some of this work has been supported by NSF. And with that, thank you for your time, and I'll be happy to take any questions. Well, I'll start with you.
Oh, sorry, that's the other one.
Let's go. I'll get back to you, Dr. Hayes.
I just want to ask what the slide you showed where you had bubbles rising hitting the electrodes, and you said some of them passed through and some of them crashed into the electrode. I'm curious, what are the implications of the bubble sort of gathering around the electrode? What does that imply? What does that lead to?
So are you asking from a DNS perspective or from the plasma perspective?
It's from a plasma perspective.
Okay, so if the bubbles are, I don't know, from a plasma perspective, it just essentially informs our frequency of these voltage pulses. So then it's not like we're like zapping the water continuously, right? So there's a frequency that we want to set. So if we know how long the bubbles are at the electrodes, we have kind of, I guess, more leeway when we're setting up the frequency, and it's easier to kind of match the voltage pulses with the bubbles hitting the electrodes. So if they're there for ages, we can be kind of relaxed and do 1 or 2 even pulses, every millisecond or whatever. But that's the discussion there.
Thank you.
Charles?
Was there a preference over a box to wire contact or a wire contact with the bubbles? Was that does that depend on application?
So you're talking about the pin-to-pin versus the wire box?
Versus one wire.
So that, I don't think there was a preference. It was more that I went rogue and tried the pin-to-pin geometry and it worked. And there was a lot of difficulty experimentally getting that wide cylinder geometry to work because essentially the bubbles weren't seeing the ground. So you need to bring the ground closer, and then there was like weird air gaps on the side of the test tube, I think is where we ended up with. And so there'd be more activity in that air there than in the actual bubbles. And so it's more of what's easier to get done. We'll go to Dr. Hayes' question maybe. And Mario, could you read that out? Awesome. See if I can get it there. I can pull it up. So Dr. Hayes' question is on the screen. I'll read that. Would it be possible for you to contextualize any kind of levels or quantitative improvements in BWR heat transport estimations that this research might enable? Oh. I would say that's definitely outside the scope of what I'm doing right now, but we could potentially discuss that offline if you're interested, Dr. Hayes.
I mean, I cannot generally,
Okay.
these methods that's what we use for the LWR research, and Castle was a big part of looking into it. And so not exactly what Naveen was doing, but fast interface capturing does allow for evaluating heat transfer improvements, things like that. In fact, I have another student working on a heat exchanger design with industry support. So things like that are totally possible.
Yeah, if you're not worried about plasmas, I mean, I guess I'm just sitting here wondering how that applies to. But yeah, in terms of using DNS to look at the void fraction, the shapes of the bubbles near the walls, and so on, that's been done a lot, and especially in our group even. And there's a question over there.
Can you go to page 9?
Yeah. There you go.
What is the last equation? What are that?
This one?
Yeah.
This is the viscous stress tensor. And so this is essentially what we use to look at how the velocity, the viscosity kind of diffuses it's kind of the diffusion term in the Navier-Stokes equations. And so
this tells us it's a Newtonian fluid. And
yeah.
Typically it sits inside the equation, and sometimes it's not even separate. Sometimes it just separate.
Yeah, but yeah, it's just looking at where the viscous stresses are.
In slide 28, I had a bit of clarification about the graphs.
Oh yeah.
So Y was vertical, was X in the same direction as the rods, or X was?
No, Z was in the same direction as the rods. X was perpendicular.
Okay, perfect. Yeah, that makes sense.
Yeah, there is a little.
Yeah, I just noticed a little coordinate axis up there.
Yeah.
So for the bubble simulation, you are solving N's equation for the air or for the water.
Could you repeat that?
For you are modeling bubbles,
Mhm.
so you are solving the NS equation. That's for air or for fluid.
Oh, the Navier-Stokes, and the INS is solved for both. So we use the level set method, which is a one fluid method. So what you have is essentially one set of equations for the whole fluid, both the air and the liquid. And then so near the interface, the properties are smoothed out to go from properties of air to the properties of water.
Okay.
Any other questions? Sure.
There's just one more. How often did bubbles pass through the way you want them to?
Not very often. So when we looked at experiments, I mean, and this has been ongoing development, maybe once or twice a second, which, I mean, these bubbles are probably going through at 60 hertz. So it's not too often, but when you have that kind of super sporadic stuff and you're trying to time it with, say, 60 hertz pulse, things get a little bit difficult. And so we're looking at kind of timing that so we can have a voltage pulse as the bubbles passing through.
Any more questions? Well, if not, let's thank Naveen again. I think it was actually,